Hello, we are Memphis Communiversity and we are back doing another calculus done wrong lesson where we wrong calculus before calculus wrongs us. Today what we're going to be talking about is we are going to be talking about concavity, which is another property of shapes and curves. So it's going to be very similar to our previous video. Our previous video was on increasing, decreasing functions. What we talked about is we drew a sine chart of f prime to determine a property about the graph of f. And we're going to be doing the same thing here, except we're going to be doing the second derivative. So our goal will be to take the second derivative, draw its sine chart, and that'll tell us about a property about f, mainly concavity. So we are going to be drawing a lot of sine charts. So if you haven't watched our sine chart video, we draw them not with plugging in numbers in the interval because we think that's dumb, not dumb, but we're not calculators. We're going to mess that up a lot of times. What we're going to do is we're going to do the safer option, just know how to draw these general polynomials. So watch out that sine chart video if you want to. Watch the increasing decreasing video if you want a similar lesson, but with f prime instead. But now for this new lesson, let's do f double prime. So f concave up or down, that's what we're going to talk about today. F concave up, f concave down. So before we start, what I want to talk about is I want to talk about what concave up or down looks like on the graph of f. Keep in mind that we're never going to draw the graph of f ever again in this video, but it's nice to know the notion of concave up or down also in inflection point. So before we start the rule, let's start off with a function of f, a graph of f. This is going to be my nice graph of f. So what does concave up or down mean? Concave up or down is not too crazy of a term. All it means is that the slope on the interval is getting bigger. So for example, let's take this portion of the graph right here, nice and pretty. What you do is, if you look at the slope here, the slope is around 0, if you notice my marker here. And as I'm going towards to the right, as I get bigger and bigger x's, my slope is getting bigger. My slope is around 1, my slope is around 2, my slope is around 3. So as I'm going over here, the slope is getting steeper. I'm getting steeper up the mountain. That's what concave up is. Same thing with the negatives actually. If you approximate the slope that's around like -4 maybe, then as you're going towards bigger and bigger x's, which is how we normally read numbers, you're getting bigger and bigger and bigger slopes. -4, -3, -2, -1. So what we're doing is we're just getting steeper and steeper and steeper and steeper. So this is what is called concave up. F is concave up. And then what concave down looks like is this thing right here. That's when your slopes are getting less steep, when you're getting smaller and smaller slopes. So instead of slope 4, we get slope 3, we get slope 2, we get slope 1, we get slope 0. Same thing with the negative sides. We're going to get slope -1, -2, -3, -4. So this is what is concave down. A lot of times students remember that F is concave up when you're literally like a U for up. When what I say is you're eating the sky, the mouth is open towards the sky. It looks like a regular parabola here, an upside down hill. Concave down, it looks like this, of course. You're eating the floor. You can just draw an arrow. What is this open towards? It's open towards the down part of the world, whatever. So I don't know what I'm saying anymore, but notice that it is open towards the down. It's eating the floor, so this is concave down. It looks like a hill. Concave up looks like a valley. Then there's this thing called the inflection point, which is around right here. So this is what is the inflection point. And as the name might imply from English, the inflection point is when it changes from concave up or concave down. So instead of the slopes getting smaller and smaller and smaller, the slopes are getting bigger and bigger and bigger. So this is again what concave up or down looks like on our graph of f. But remember, we're never drawing the graph of f. We're instead going to draw a sine chart of f double prime, because it'll be difficult to draw the graph of f in most cases, but it'll be easier to draw the sine chart of f double prime, and that's what it's going to tell us about whether this graph looks like a U or whether this graph looks like a upside down U without actually having to draw it. So that's the magic of this. So let's talk about the rules being the most important part of this video. So erasing this introductory picture, let's go for my favorite thing, the rules. So important that you should probably have them tattooed somewhere. Let's talk about them. So F is concave up when F double prime is positive. And there's another rule as well, unfortunately, which is where F prime is increasing. Let me write down the rule for concave down, and then let me explain it a little bit. F is concave down when F double prime is negative. So it's just the reverse of the previous thing. where f prime is decreasing. So, concave up or down, in my opinion, is a little bit easier because you're always dealing with a second derivative, and the second derivative is often simpler than the first derivative. But unfortunately, there are two rules for concave up or down. There's f double prime being positive, and there's also f prime being increasing. So the question is, why are these rules a thing, and when do I use each one? So again, what did I talk about f is concave up? That just means your slope is getting bigger and bigger and bigger. What is slope? Well, slope is the f prime. So it makes sense that f is concave up when your slope is getting bigger, when f prime is increasing, because that is the slope. But in our previous video, what we learned is that any function is increasing when its derivative is positive. So what is the derivative of f prime? Well, it happens to be f double prime. So there's two equivalent rules. F prime is increasing means that f double prime is positive. So both of these things are true. They sort of come from each other. Same thing with f concave down. That means when your slope is decreasing. So f prime has to be decreasing, but there's a rule that any function is decreasing when its derivative, which happens to be f double prime, is negative. So we have this rule and this rule. So this is why the rules are generally why they are, but the question is when to use each one, and that's what students sometimes confuse. So in this video, we're actually only going to be exclusively doing one rule. We're only going to be doing f is concave up when f double prime is positive, or f is concave up when f double prime is negative. Because remember that when we can take derivatives, the only thing we know how to draw is sine charts. We do not know how to draw increasing and decreasing charts. They're not a thing. We only know how to draw sine charts. So we always want to compare positive and negative. So when I see these questions, when I see f concave up, when I see f concave down, and I can take derivatives, I'm going to automatically take two derivatives and try to draw the sine chart of that derivative. That's what we're going to be doing throughout this video. There is a rule that we're going to neglect a little bit in this video, which is that f is concave up when f prime is increasing. That's certainly true, but we're going to only apply that rule when the graph of f prime is already provided. That does happen, of course, on free response questions when they give you a graph of f prime. Then it doesn't really make sense to involve f double prime, so we're going to use that rule then. But that's another video in the future. So again, two equivalent rules. F is concave up when f double prime is positive, f is concave up when f prime is increasing. When you can take two derivatives, use this rule. When the graph of f prime is already provided, use this rule. In this video, we're going to be focusing on this. Then there's the notion of inflection points, but that's not too bad as well. It does unfortunately have two rules as well, but hopefully you can tell when to do which one. So f has an inflection point. Let's actually write it out. Again, this is when f changes concavity. Concavity, don't know about concavity, even if that's the lesson for the video. There's going to be implications for each function. So it's when f changes concavity. So the one we're going to be using the most often is going to be something that involves f double prime. It's when f double prime changes signs, meaning that it goes from concave up to concave down, or concave down to concave up. Another rule is when f prime goes from increasing to decreasing, or decreasing to increasing. But again, we're not going to use that in this video. We would only use that if we're provided an f prime graph. So f prime goes from increasing to decreasing, or decreasing to increasing. And sorry, I'm going to abbreviate. Don't be lazy like me. You should probably write out the word increasing or decreasing. You should definitely write f prime, f double prime, and things like that instead of slope, it, blah, 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 blah. These are the rules. Get to know them very, very well. Let them become your friends. And then let's try to do some examples. So copy this down. If you want to pause the video, that's certainly fine. I'm going to go for examples because I'm pretty excited. So let's erase this now. Just know the rules very, very well, and they will guide you to victory, whatever victory might entail. So all my questions today will be f is concave up or down, and also inflection points. So we can write f concave up or down, or inflection points. So usually your question is going to be, here's f, now go for two derivatives, draw the sine chart. But let's start off with a little bit of a warm-up question, a little gentle introduction where instead of having to find the second derivative, I'm going to be somewhat generous and I'm going to already provide the second derivative. So let's suppose that the second derivative is going to be e to the x, 5 minus x. Let's do, I don't know, x squared minus 4. squared, and then I'm going to do x plus 1 to the third. So this is going to be my function. Pretty complicated, but I didn't have to find this. I just made this off the top of my head. So let's get going. So the thing that we try to stress the most in our increase and decrease in the video, also our sine chart video, is that I want to draw the sine chart of this. But before you draw the sine chart of this, be patient. I know you're excited, but you want to factor everything as much as possible. And what do I mean by factor everything as much as possible? I want everything to be able to form x plus or minus something, x plus or minus something, x plus or minus something. So first off, we have this 5 minus x. I don't like that. I don't want a number minus x. I want x minus a number. So what I'm going to do is I'm going to perform a little switcheroo. Just switch these guys. You're not allowed to switch things arbitrarily, but this thing is equivalent to the negative of x minus 5. So this is going to be negative x minus 5. We'll rewrite the a to the x. So that's that. So again, this form is a lot easier because it's not hiding this negative, and this negative is crucial when we ask the question, positive or negative, to draw the sine chart. Then this guy looks factored, x plus 1 cubed, so we can rewrite that. This is not factored. X squared minus 4 is probably the most common thing that you're going to factor. It's x minus 2 times x plus 2, of course. So it's going to be x minus 2 times x plus 2. We're going to square it. So again, this is still not factored as much as possible. It's not x plus or minus something, x plus or minus something, x plus or minus something, because it's x plus or minus something squared. So what I'm going to do is I'm going to break this up, because if you have a product squared, that means that you're just going to take one thing, square it, multiply it by the second thing, square it. So in this case, we're going to have this form right here, x minus 5, x minus 2. This is going to be squared, x plus 2, also squared because they were a little bit of a pair. How nice and lovely. And then we have x plus 1 cubed. So this is going to be the thing I'm going to try to draw the sine chart of. Now let's get going. Hopefully you know that e to the x is always positive. Remember, we're not drawing graphs. We're sort of taking a shortcut. We're just drawing sine charts, a much easier thing. So e to the x doesn't affect the sine chart of this at all, because e to the x is always positive. Even e's to negative numbers are always positive. So in this case, we're going to just x this out. So all we have to do is draw the sine chart of this long polynomial right here. So let's get going with our normal sort of process. What I do is I first count the number of zeros, including the exponent. So if something has a power of 2, it contributes 2 zeros. This one will contribute 3 zeros. So let's count. Looks like we have 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be something that's even, either a parabola or an upside down parabola. And what we do is we look at the number in the front, determine if we have a upside down or regular parabola. In this case, we have a negative. This negative, again, was super crucial. It came from the 5 minus x and rewriting it. That's why it was an important step. So it looks like we have a negative even thing. What is a negative even polynomial? Well, that's going to be an upside down parabola. That's going to be your hill. So it's going to start right here and right here. As so. Now what you do is you plot the zeros. Looks like we have 4 zeros here, and we're going to obviously sort them in order. So it's negative 2, negative 1, 2, and 5. So it's going to be negative 1, negative 2, 2, and 5. Don't know why that took me so long. So we're going to start at the bottom, end at the bottom. And then how do you do zero behavior? What you do is as you approach a 0, you look at the exponent of that factor. If it's odd, it'll just go straight through. Or if it's even, it'll bounce. Little bouncy bounce. So in this case, we're going to start it again in the negative side underneath the x-axis, because this is a negative parabola. It starts and ends below the axis. Then as I approach negative 1, I'm looking at this number. It's cubed, so that means it'll go through. So it'll nice and go through. Then at 2, or negative 2, it'll bounce because this is squared. So let me just try to draw this. It's going to be a bounce. Then at 2, it's going to bounce again because this is still to the even power. And then finally, what is this? This is technically to the 1. So it looks like it's going to go through at this final point, which is great news for me because it ends up where I want it to end up. So I feel like I'm doing it correctly. This is an upside down parabola. Starts at the bottom, ends at the bottom. Remember that this is a sine chart of f double prime. It's not actually about the function we care about, which is f. We're never going to draw the graph of f, so do not focus that these look like hills. You might think that this is concave down because this is eating the floor, as we like to say, but remember that this little squiggly line thing is only beneficial so that it tells me the signs. I don't want to focus on it. I want to focus that this is positive, 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 negative, negative. Looking at this graph and trying to determine whether it's a hill or a valley would tell you about the concavity of f double prime, but we don't care about that guy. We care about f is concave up or down. We want to know whether f double prime being positive or negative determines f being concave upper. So let's write the answers. Just like normal, it's always going to be a format of 3 things: question, justification, answer. Sort of like if we were in like 4th grade English, we want to write the question and the answer, just to remember good times. So f is concave up. I like to write the justification first to build my confidence. That's where f double prime is positive. This is the rule. And then where is it positive? It looks like it's going to be on these 3 intervals because that's literally where there's pluses. So it's going to be -1, -2. We can separate it by commas, not to be too crazy. 2, 5, and finally, did I forget one? I forgot -1, -2. So let me not forget that. -2, and then 2, 5. So that's that one. Again, f is concave up when f double prime is positive. It's literally where it's positive. Now let's do concave down. It's going to be the negative portions. So f is concave down when f double prime is negative. That's going to be on negative infinity to -1, the left side of this sign chart and also the right side of this sign chart. So on negative infinity to -1, you could also say like x smaller than -1 and 5 to infinity. Finally, let's do inflection points. It is annoying to write all this stuff, but sometimes we have to do annoying things so that we benefit from them maybe. I don't know. So let's do f as an inflection point. I'm going to abbreviate it as inf point, but that's because I'm running out of space. Try to not do that. That's when f double prime changes signs. And so where are they? It's going to be at -1 and 5. So these are often multiple choice questions where the answers are pretty tricky. I try to trick my students because I'm a terrible person, but for example, I would have one of the answers as -1, -2, 2, and 5, all of these zeros. And then I'll have a second answer that would say -1 and 5 only. And that would be the correct answer because it bounces at -2, it bounces at 2. That does not count as an inflection point. It has to actually go through, so it's these 2 answers. So this is how you do these concave up or down questions. You take 2 derivatives, but in this question, the second derivative is already provided. You want to factor it as much as possible. And then you draw the sign chart, just like we did with the sign chart of f prime in the increasing decreasing video. But instead with f double prime, then you just write the rule. If you had the sign chart, you shouldn't miss it. Just look at positive and negatives and things like that. So now, this has been a long warm-up question, but let's try the actual question where we start off with f. It shouldn't be too bad. Let's do 4 or 5 or so, maybe some weird ones. Let's just get started. Let's not sort of drag all of this out. Don't know what I'm saying anymore. Let's just get going to the good stuff, the actual questions. So in this case, we're going to do f of x is equal to, let's do x to the 4th, and then we're going to add 6x cubed. So this is going to be my first question. Where is it concave up? Where is it concave down? Inflection points. So first thing, again, there is a rule where f prime is increasing or decreasing, but you only use that for f prime graphs. If I see the word concave up or down, if I see the word inflection points, I automatically go for 2 derivatives. If this were a free response question, I might actually get points for just literally taking 2 derivatives, even if I have no idea what concave up or down is. So let's take the first derivative, and then let's take the second derivative. So for this first derivative, it's obviously the power rule. You take this little exponent, you drag it to the front, you subtract 1, so it's going to be 4x cubed. Then, same thing here, you bring the 3 to the front. There's already a 6 there, so let's let them get to know each other. That's going to be 18, because 6 times 3 is 18. Then we have x squared. Then we do it again, because again, automatically go for that second derivative. So in this case, the 3 drops down to the 4. They meet each other. That's going to be 12x squared. Then the derivative of plus 18x squared. bring the 2 down. I believe 18 times 2 is 36. So this is going to be 36x. When we have this question, we are now ready to draw the sign chart, but we're actually not ready to draw the sign chart because we want to factor everything. This one shouldn't be too hard to factor. We're going to take out a 12x. We are going to be left with x plus 3. So now we are ready to draw the sign chart. So I'm going to list out these zeros. Looks like we have -3 and 0, and we're obviously going to put it in that correct order. -3 and 0. The key is that we don't teach to plug in an interval, a number within each interval. There's 3 intervals here. Some teachers teach like plug in the number 1, plug in the number -2, plug in the number -5. But we're not calculators, so we're probably going to mess it up. We're going to just draw a normal sign chart by counting things. So notice that this is even. 1, 2, 12 does not contribute a 0. So this is one of the most common sign charts. This is just a nice little parabola, positive. So it's a nice little parabola. And again, we don't actually care about the parabola. You might think that this function is concave up or down, or concave up everywhere because it's an entire U. But remember that this is a picture of f double prime to tell us a picture about f that we're never drawing. So this is f double prime. We don't care about this actual line. We only care about that this is positive, negative, and positive. The line tells us the signs, and that's the important thing. So let's go for the answer. Again, it's f is concave up. Try to not be lazy as me. Let's actually write out the word. But it's f double prime is positive. Looking at this, it looks like it's negative infinity to -3. And then let's not forget this portion, 0 to infinity. And then where is it concave down? Well, f is concave down when f double prime is negative. Hopefully you know these rules already by heart. They're so important. They're so fun to learn. Maybe, I don't know. F is concave down. That's on f double prime negative. That's from -3 to 0. And then finally, let's do inflection points. They're not too crazy. F has an inflection point. We should justify our stuff even if it's super annoying because we want to tell the world what we know and we want to show why we know it. So f inflection point is f double prime changes signs. Let's see if I can squeeze the answer in here. Looks like both of these zeros, it changes signs, meaning f double prime because it goes through and it goes through. It doesn't matter if it's positive, negative, negative, positive, as long as it changes signs. So in this case, it's x is equal to -3 and 0. So not the craziest question in the world. Again, nothing too crazy. That's what I just said. Right when you see a concave up or down question and you're listed out the function, just automatically take 2 derivatives, factor the derivative as much as possible, then draw the sign chart based off our sign chart rules. This one is even and positive. That's a little parabola. Then once you draw the parabola, focus on the positive and negatives. That will guide you to the actual answer. F is concave up when f double prime is positive. F is concave down when f double prime is negative. So these are the questions, and you can tell that I think they're a little bit easier again because the second derivative is often simpler than the first derivative. I'm more willing to take another derivative if it means that my sign chart will be simpler. So usually students don't miss these questions. They only miss the questions, not if they're hard, but if they're a little bit tricky and weird. So let's practice one of those. So I'm going to erase this right here. I'm going to erase this. Let's erase our inflection point. Let's be lazy and not erase our question and justification because that's going to be the same thing. So we'll erase these guys instead. And then we are going to erase this. And instead of x to the 4th plus 6x cubed, let's do a pretty similar question, but instead change it to x squared here. So this is going to be my next question. No matter what it is, still when I say concave up or down, inflection points, I automatically go for 2 derivatives, sort of my natural instinct on how to face the world. So in this case, it's going to be 4x cubed again, but now when I bring down the 2, it's just going to be 12x. I'm going to take 2 derivatives automatically. I never stop at the first derivative. So it looks like it's going to be f prime, double prime of x. Again, power rule, 12x squared plus 12. If you want, you can factor this as taking down a 12, x squared plus 1. So now we are ready to draw the sign chart because we found the second derivative. But this question is a little bit weird, x squared plus 1. If you know the graph of x squared plus 1, x squared plus 1 never crosses the x-axis. It's actually a parabola, it's just shifted up 1. If you try to solve this, if you did a little bit of math on the side, you would get x squared plus 1 is equal to 0. So x squared is -1. So x is equal to plus or minus the square root of -1. But you can't take square roots. This is single variable calculus. I don't want to introduce complex numbers or i's. Usually they never occur, and not usually they never occur, but they never occur in these single variable calculus questions like the AP calculus exam. So basically, this sign chart is kind of strange. It never crosses, and sometimes students confuse what's the actual answer. Well, again, just focus on the positive and negatives. Where's this sign chart positive? It's positive everywhere. If you plug in any number and you square it, even if it was a negative number that you plugged in, once you square it, the negative goes away, you add one, this is never even 0. So in this case, this sign chart is always positive. So what's the answer? Well, f is concave up when f double prime is positive. Where is this positive? Always. So what you can say is from negative infinity to infinity, every single number in the world. If you want to write a fancy R for all real numbers, you can do that. So all real numbers. When is it concave down? Well, it's never negative. So in this case, when is this function concave down? It's nowhere. So for no x's. So you can see that this question was the same thing. We just hit a weird sort of sign chart. This would occur as well if your sign chart was just the number like 12. If your f double prime of x was equal to just the number 12, it would always be positive, just like this one. The answer would be all real numbers. So hopefully you can see that even if you hit tricky questions, just use our rules, look at sign charts, just see positive and negative, and you should be able to figure it out. Now, let's do some harder questions. But remember that the hard part about this is probably not the actual rules themselves, the thing we're introducing. It's probably just taking those two derivatives and then drawing the sign chart of that second derivative. So I have 3 more questions that I want to do. I want to do one with an e, I want to do one with trig, and I want to do one with a fraction because those are usually the ones that people have the most trouble with. Before we talk about that, I forgot one thing, the inflection point. Where is it an inflection point? But hopefully you see that this one has no inflection points because f double prime doesn't change its signs. So it's when f double prime changes signs. But this does not occur, so there's no inflection points. But again, I don't really want to focus on this question. I want to do some with harder derivatives just to spice up life a little bit. So let's start with some more, a little bit of harder question. Some e's, some trig, and some fractions. So let's erase this. We're still doing concave up or down, and let's do this function instead. E to the minus x times 3x. So I'll let you pause the video, try it for yourself. I'm going to cover my A's for 3 seconds, 1, 2, 3. Hopefully you had a chance to try this one. Let's do this one together now. So automatically we take 2 derivatives, but we're still taking derivatives. So anytime you take derivatives, you just have to know that you might have to do product rule, you might have to do quotient rule, you might have to do chain rule. So that's going to be the scenario here. I'm going to underline this because this is going to be product rule. And then I'm going to not forget about this guy. I'm not going to let this guy escape. Keep in mind that the smallest chain rules are the chain rules that people usually mess up. This one will involve a chain rule because there's a negative x. The derivative of negative x is not 1. It does have a derivative. So let's get going. So the first thing I'm going to do is keep the same, e to the minus x. Take the derivative of 3x, which is just times 3. And I'm going to write a plus because we're doing product rule. Then, what is the derivative of e to the minus x? Keep in mind, it's not just e to the minus x because the derivative of e is that thing. Because, again, minus x has a derivative of negative 1. It's going to be e to the minus x times negative 1, where this negative 1 occurred from the chain rule. Do not forget this. This is where people mess up. It's very easy to mess up because it's so small, and sometimes the smallest things are the easiest things to miss. But if you get accustomed to just anytime you have minus x, it's times negative 1 because of the chain rule, you should be good to go. Let's finish out the product rule by keeping the same. So let's keep the same, derivative, derivative, keep the same. Looks like we are good for the first derivative. A little bit more complicated than our previous examples, but that's why we're doing this. Another thing is we're about to take the second derivative, but a rule of thumb, if you're taking multiple derivatives or if you're taking multiple integrals, it's to simplify as you go. First, simplify that first derivative before you go for the second derivative. I know we are excited, but I don't want to do double product rule, which is what I would have to do. So again, I am going to try to simplify this as much as possible. So f double prime, I'm not ready for f double prime time. I'm going to simplify this. What can I take out? Looks like I can take out an e to the minus x, even a 3 because both of these have 3's. And I'm going to be left with a Keep in mind that sometimes students, what I just did, the error that I just did is that when you take this out, this doesn't go away. I'm taking this out, so what's left there, it's 1. So just keep in mind that I'm still taking this out and something still remains, it's just the number 1. You don't want to lose this plus. Over here, it's going to be plus, and then I took out an e, the minus x, I took out a 3, so it looks like it's just going to be 1 minus x. So just be wary that when you take this out, don't forget that there will still be something in this term. So now, looks like I'm going to be ready for the second derivative. Again, this is easier inherently because it's just one product rule. Let's do that. F double prime of x. We're going to keep this one the same, so it's going to be 3e to the minus x. I can write a 3 correctly. Then I'm going to take the derivative of this, but that's just -1, so I just put a negative in the front. Then, second half of the product rule, the derivative of 3e to the minus x, but we're not going to let minus x get away. We're going to chain rule that sucker. So it's going to be 3e to the minus x times -1. And then finally, there's going to be a 1 minus x to keep the same. So as we're taking derivatives, we do not mess up the chain rule because we would be ashamed and bring shame to our families, and we certainly do not want to do that. So it was first times derivative of the second, so that was this negative, plus derivative of the first, so that's why this -1 here came from the chain rule, keep the second. So this should be right. Hopefully this is right. Now we're ready for the draw the sign chart, but again, before we draw the sign chart, we do want to factor everything as much as possible. Let's take a few steps to so that we don't miss anything. So what I'm going to do is I'm going to take out a -3e to the minus x, so it would be -3e to the minus x. Again, there would still be a 1 remaining. We took out a -3e to the minus x, so it looks like we'll just have this term right here, plus 1 minus x. I'm going to keep simplifying this as much as I can because remember the golden rule of sign charts is to factor as much as possible. X plus or minus something, x plus or minus something, x plus or minus something. So in this case, we'll get -3e to the minus x, 2 minus x, just 1 plus 1 is 2. That's a pretty easy step. But again, I do not like 2 minus x, that's a number minus x. I like x minus a number. So I'm going to change this to be, I don't know why I'm sort of moving so much, but I'm going to change this to x minus 2. A negative comes out, so we'll cancel out with this, and that's very key when we answer the question positive or negative. So it looks like our final derivative that we're about to draw a sign chart of, our final second derivative, is 3e to the minus x times x minus 2. So this is going to be the sign chart that we're going to try to draw. Now, remember that even if it's e to a negative number, this is always positive. All of this stuff is always positive, so I can ignore it. 3e to the minus x, even when you plug in positive numbers and you get e to a negative exponent, that's still positive because it's 1 over e to a number, and 1 over e to a number is positive. So really, it's just the sign chart of this little guy right here, x minus 2, one of the most famous sign charts because it's just a line. Where does it cross to? It's a positive slope line, so it goes like this, positive, negative. Let's put the negative underneath like normal. And then now we're ready for the question. So this question was really hard, obviously, going from the first derivative to the second derivative, being careful with product rule and chain rule when the need arose, factoring everything. But once you get to that factored form, you should be good to go. You draw this sign chart. Let's answer the questions. F is concave up when f double prime is positive. So that's from x bigger than 2, where you can say 2 to infinity. So I'm going to write x bigger than 2 because that could be the multiple choice answer. F is concave down when f double prime is negative. That's x smaller than 2. Another way to say this is negative infinity to 2. And then finally, what's the inflection point? Well, the inflection point is this point right here, 2, because it's going from negative to positive. So f has an inflection point. F double prime changes signs. Even when I'm getting very annoyed and I'm running out of space, I still like to justify just to build good habits, because somebody told me that building good habits is important. F double prime changes signs. That's at x is equal to 2. So even in these more complicated questions, where we have to do the product rule, we have to deal with these weird negatives, we took out some stuff to make the product rule a little bit easier in the second step. Even in these harder questions, we should still make our way through the question. If we go slowly, we do the steps. Once we draw the sign chart, it's the same rule. So let's do a little bit of an easier question. Let's do trig. Maybe that's not easier, but let's just see what we have. So I'm going to erase this now. erase, erase, erase. So these questions are a little bit involved because you have to take two derivatives, but they are the same thing over and over and over again, so I'm not going to complain too much. So my next question is going to be cosine x minus 3x. And remember that because trig repeats over and over and over again, there's usually an interval. So let's have the interval being 0 to 2 pi this time. So what we're going to do is we're going to see where f is concave up or down and find the inflection points of this function right here on this interval 0 to 2 pi. Immediately, of course, we take two derivatives, so I'm going to do that. The derivative of cosine is minus sine. This derivative is a lot simpler. This derivative of minus 3x is minus 3 than the previous example because we didn't have to do product rule or quotient rule, chain rule or quotient rule, so I won't complain. I immediately find the second derivative. The second derivative in this case is minus cosine x. The derivative of minus 3 thankfully goes away. So I have just this simple function right here. Now I'm ready to draw the sine chart. Because we have no x's, we don't have like x plus minus 1, we don't have anything to factor. We do our trig sine charts a little bit differently. We just graph the function actually. So we're going to start at 0, go to 2 pi. You do need to know basic sine and cosine graphs, and keep in mind that this is an upside down cosine. So it's going to start right here, and it's going to go through these 2 points. This point right here is pretty important. This point right here is pretty important. This point is not as important. This is going to be, but we'll just label it anyway to help us find the other points. This point is pi, so this point is pi over 2, and this point is 3 pi over 2. Let's erase the pi because it doesn't matter in this question. Again, do not focus on the graph of this, what this actually looks like, because that's what confuses students. They'll be like, oh, it's concave down over here because it looks like a hill. It's concave up over here because it's eating the sky. It's part of views. But remember that, again, the focus on is literally where things are negative and positive. It's negative here, negative here. So we should be ready for the answer. So where's f concave up? That's where f double prime is positive. Not focusing on this squiggly line, I'm only focusing on the positive and the negatives. So it's from pi over 2 to 3 pi over 2. So we'll write that with parentheses like normal. Where's f concave down? Well, that's where it's below the graph. F is concave down when f double prime is negative. Just keep repeating these rules over and over and over again, and you should sort of hammer them into your brain, if that's a phrase. 0 pi over 2, and then 3 pi over 2 to 2 pi. We do, of course, don't do the entire number line because we're only on this interval. And then finally, what is the inflection points? Well, the inflection points are going to be this point and this point because they're going through, they're not bouncing at these points. So f has an inflection point. Inflection point, again, even if we don't want to, let's just keep writing the justifications. We'll probably be able to remember them more if we just keep practicing them. In this case, it's pi over 2 and 3 pi over 2. And 3 pi over 2. So, again, promised one last question. Let's do a fraction question, but this fraction question, this e question, this trig question, they're not any different. You just take derivatives carefully, draw the sine chart, and you'll be good to go. So let's do one more question, a fraction. So I'm going to erase this. Erase. Let's try to be a little bit neater with our work, but no guarantees. What should we do? I'm going to do the function, let's do x minus 3 squared. And then let's do a 5 on top. So I'm mainly doing this question just to practice derivatives. So the first instinct, concave up or down, is to take two derivatives. The one thing you don't want to do in this question is do the quotient rule. That would make it look really, really nasty. Remember that if there's x's just in the denominator or the numerator, it's often good to rewrite it and it'll make the derivative a lot easier, especially because we have to take two of these bad boys. So I'm going to rewrite it as 5x to the minus 3 to the negative 2 so that I can use the power rule instead of the quotient rule. So let's lower this f prime of x and f double prime of x so I have space. So what's f prime of x? All you do is you drop the negative 2 to the front. So it's negative 2, x minus 3 to the negative 3. Notice how easy it was for me to draw this because I'm doing the power rule instead of low d high minus high d low over low low. That would be so annoying. And it also makes the second derivative a lot easier as well. Just keep dropping the power. So it's going to be 30 x minus 3 to the fourth. Now we are ready to draw this negative 4. Not ready. Sort of yelled there, but it's negative 4. Now we're ready to draw the sine chart. Remember, the rule is you use negative exponents to employ the power rule so that you can take derivatives. But once you're done with that, it's often good to rewrite it as a fraction. So it's going to be 30 over x minus 3 to the fourth. Some people get a little bit intimidated with these fractions, but the sine chart of fractions, because we're drawing sine charts and not graphs, it's going to be the same as normal. So it looks like we only have one 0. This 0 is the 0, 3. Let's count. 30 does not contribute an x. Be careful with that. It's only this thing. The things with x's that contribute x's contribute zeros. So it looks like we have 4 zeros here. There's no negative because the negative canceled out because we introduced a negative, but then it canceled out when we brought the next derivative. So we're dealing with something, parabolic that's positive. So it looks like this. It's basically going to either go through or cross at this point. But as I approach the 0, because it's even, it's going to go balance. Don't know what I'm saying anymore. Last question. But we have a strange little sine chart, but this is sort of like the question that we had previously. Let's label things positive, and let's go for the answer. So where's f concave up? It's where f double prime is positive. So it's going to go from negative infinity to 3, and 3 to infinity. Let's ask this question one more time. Where's f concave down? It's where f double prime is negative. It's nowhere. Because there's no portion, I don't look at this picture, but there's no portion of the sine chart that's negative. F concave down is negative. So it's no x's. Same thing with the inflection points, because remember, if inflection points aren't just the zeros or where the f double prime doesn't exist, it actually has to go through. So in this case, because it bounced on the sine chart, there's no inflection points. F inflection points. F double prime changes signs. So there's no x's as well, and we're good to go. So that's our concave up or down video. Hopefully this has been useful. Anytime you see the words concave up or down and you can take two derivatives, just automatically take those two derivatives. Then factor that second derivative as much as possible. Draw the sine chart. The rule is f is concave up when f double prime is positive. Then the second rule is f is concave down when f double prime is negative. There are alternative rules which we'll talk about in future videos where we are provided a graph of f prime. That's f is concave up when f prime is increasing. Check out our future video. I believe there'll be something called Introduction to F prime graphs or something where we'll use that rule to do those concave up or down questions. If you want to practice more algebra questions like this, taking two derivatives, of course we have a Girls Teach Calculus video. I'll link it in the description below, where one of my former students practices a lot of these examples. She does simpler ones. She has ones with weird sine charts that never cross. She has ones with e to the x's, trig, fractions, chain rule, product rule, whatever you can name, she has it. So be on the lookout for that. Go check that out if you want more practice. Our next video is going to be on relative extrema, relative max or min, local max or min. So it'll be very similar to this process where we'll go back to the first derivative. So check that out if you want to continue along with us on our exploration of shapes of curves, knowing what the graph of f looks like without ever having to graph f by instead drawing the sine charts of f prime and f double prime. But thanks again for watching. Like and subscribe if this video was useful for you at all. I hope to see you next time as we do relative extrema. Thanks again for watching.